Okay, so we'll get started. So, how many of you have read this New York Times today? You have no homework, you should at least be reading New York Times, right? So this was, on the front page today, I think. At least it's on the front page of the internet one for a while, and then it's circulating in the front of the printed version. So this one just says, close says Google, but shop signs say open. And the story, those of you who have read it, is Google has this thing called Places. You can take over. And then sorry for that. Sorry.
It's okay, I'll come.
Google has this thing called Places, and you can actually give information as to whether a place is open or closed. Crowdsourcing. Now, it turns out that essentially a huge number of places which Google says are permanently closed are actually open. And they're wondering why nobody is coming to have food in them, etc. And, obviously, it's a classic example of what? So what cardinal principle we talked here is being violated by Google thinking that people will give free information about whether or not stores are open.
The other stores are open. I have done that.
That's the big idea. It's a jungle out there. It's adversarial. Okay, and this is just the latest of the examples of if search engines are depending on human goodness, which actually doesn't exist. Because especially behind the screen, so for example, many people who don't like, let's say if I have another coffee store right next to this coffee store, I want to see this closed so that people will come to me. So I just go and say, here, it's closed. And you want more votes? Yeah, my wife, my son, everybody will log on and say, that guy is closed. Okay? So the question again is, remember, how do you make sure that freely submitted information is actually trustworthy? And they are not making sure, and so that was the issue. There was another variation on this. So for example, for a while it used to be the case that if you click on the ad and you get to the site, the AdWords, and you go to the site, then essentially the advertiser has to pay a certain amount of money to Google, our search engine. So if I want to run you are my competitor, I want to run your advertisement budget down in like a day or two. What do? I'll have my bots clicking. So that, very easily your advertisement budget goes out the window, yes?
But there are spam filters too.
It started afterwards. So the general assumption in internet seems to be not to follow this. Essentially act as if people are going to be nice until New York Times writes an article, saying that you're being stupid, and then say, oh yeah, I will fix it just now. You see what I'm saying? So, but that's the reality, web is adversarial, and if you somehow thought that you can get by with, thinking that people will be nice, then you'll pay for it, So that's an example. I think there's an advantage for running a course where New York Times works with you and writes articles that I can just show in the beginning of the class. So in fact, I think if you're not doing anything else, you should be reading, popular press, I guess. Okay, that's about that. Couple of things. After today's class, you will be, I think after today's class, you'll be ready to be able to do the project part 1. Okay. So in fact, between now and next class beginning, I would have put the project part 1 up officially. And it will be mostly, the easy part, it's essentially, it will give you a crawl of documents, and it will also give you an index, and then all you have to do is essentially use the index to, compute vector similarity, which we're going to discuss today. Okay, so that's what you're going to do, and then so that particular thing will be up by next class beginning. One other thing, if I forget to, I probably should send this mail to people general, but since everybody's here anyway, if you are printing slides, I mean, I kind of should have said this in the beginning class, but maybe I didn't say it. If you're printing slides, there are two things you should keep in mind. First of all, I tend to have one set of slides for a whole topic. And so I wind up sometimes going back and adding slides after the class is over to reflect the discussion we had. That's something to keep in mind. And the second, the big thing to remember is never print, the hidden slides. Because there's a large number of slides there which are never shown. Okay, so if you just, if you're in PowerPoint and you're printing slides, then you will get a whole bunch of extra things. It's not that it's a bad thing, you will learn more stuff, but at least you would think that why did he go from this slide to this other slide to this slide? Well, it's because I didn't go to the middle one, in the class I did it. So a whole bunch of slides are hidden, and I just leave them hidden there. So when you're printing, make sure that you don't print the hidden slides. So there's a way of doing it in PowerPoint. And same thing when you're watching the slides, do it in the slideshow mode so you won't see the hidden slides. So you will know for sure what I've shown you here. Okay? So just keep that in mind. And then once the topic is over, that's when the sides are stable. That's for sure. But it's okay if you want to print something, you can bring it to the PowerPoint. Okay, so we were talking about bag similarity last class, where documents are seen as bags and queries are seen as bags, smaller bags, and we are computing the similarity between two bags, right, using Jacquard similarity. And we could do normalization of the bags, normalization of the similarity, that's what we were talking about here, okay? So in some sense, it's as good as it gets. When we go to vector similarity, one of the interesting questions you have to keep in mind is why do we need one more similarity measure? Okay, I will answer that question sort of today, but it will really become clearer as we go forward. In essence, the view of vectors, the short answer is we know a lot more math about vectors. Okay, if you view pages as vectors, then one of, the entire linear algebra is at our fingertips now. Okay, we don't have an algebra of bags. We have an algebra of vectors. And in particular, one of the most important aspects of linear algebra, all of you should have done linear algebra, right? So do you guys remember this notion of rank of a matrix, for example? Okay, and if a matrix has a rank less than its size, that means what, for example? That means the vectors are linearly dependent. Okay, one central issue in linear algebra is independence, linear independence of vectors. And it becomes very important for us, if we are viewing documents as vectors, then there's this very interesting question as to, for example, a lot of independence assumptions get made in assuming they are vectors. And if you want to improve on those independence assumptions, you need to use linear algebra, which will tell you, which gives you some ideas as to how to capture dependence between vectors. So that's really the reason why we use vector similarity. Not because if everything else is same, vector similarity is somehow more good at capturing the similarity than the bag similarity. It is the additional mathematical operators it provides, because we make a huge number of assumptions, which we make here too. For example, it's one thing, so you can say this even here, it's one thing that as long as, if you think of bags as, this is made up of 5 apples, 4 oranges, and this one is made up of 3 apples and 2 oranges. This is the kind of bags we have looked at, okay? Now, of course, if you have, a bag of words, okay, for example, in fact, how about, if you have the fruits in here, 5 oranges, 4 navel oranges, 8 tangerines, and 3 nectarines. Okay, and then I have another bag which says 14 nectarines and 3 tangerines. And a third bag which says, let's say, 85 oranges what would you say? You know, we got into a fruit market today. But the point is, if you know your fruits, you know, which bags are more similar to each other? None of them are equal. Would you say, compared to this bag, is this bag more similar or this bag more similar? So one has 4 oranges, 5 oranges, 4 navel oranges, 8 tangerines, 3 nectarines. The other one has 14 pears and 3 tangerines. The third one has 85 oranges and 3 nectarines. And one can argue, you know, if you are from the Florida citrus growing region, that this is a citrus bag, mostly citrus. It's all citrus, you know, orange, navel, orange, you know, tangerine. And this one is orange too. So really oranges and oranges, those two bags are very similar. Okay? Now, that argument assumes, that argument violates an implicit assumption we had before, which is all fruits are orthogonal to each other. They have no connection with each other. If you eat 18 oranges, you will still not know anything about a tangerine. Do you understand what I'm saying? So bag similarity assumes all fruits are orthogonal. But fruits are dependent, fruits are correlated. Some fruits, and so when the correlation exists, then if you take the correlation into account, you may be able to tell the similarity better. In some sense, that's also true for words. You know, if you think in terms of, you know, files of words, you know, bag similarity metric is going to look at each word to be an independent word from every other word. But computer always seems to go with science. Right? Data seems to mostly go with structure. You see what I'm saying? So words are correlated. And if you're not capturing that correlation, then in essence you're not capturing the similarity as well. Okay? When you want to do that, then you essentially need to think about dependencies between terms. Dependencies between terms. And when you do that, the mathematics of linear algebra, and basically linear dependence, linear independence between vectors finds it being very helpful. That's like 2 classes from now, maybe 3 classes from now. But that's the reason why we like vector similarity, which everybody uses. Okay? So that's it. Okay, so, but you know, thinking of them as vectors are not that hard really, because if you go back to this picture, right? So here are the terms, here are the documents. Okay, we just chose to think that this document is a bag of these terms. But without changing anything, I will also like to say that this document is a vector in these dimensions. Each term is a dimension. So obviously, these are not vectors that you can draw or even visualize in MATLAB, right? Because these are 1, 2, 3, 4, 5, 6-dimensional vectors. These are 6-dimensional vectors. Okay, but each document is a vector in a 6-dimensional space. It's a point in 6-dimensional space. If I view them that way, then what can I say about similarity between points in the space? So you can talk about distances, right? So for example, if I, you know, let's start thinking at the 2-dimensional case, because I get to try it here. Okay, so here is a computer, and here is science, let's say. Okay, so I can have a document B1 which says 12 computers and 12 sciences. Okay, so presumably that document kind of corresponds to that. Right? Another document D2 is 12 computers, 11 sciences. Okay? So if it is 11 sciences, presumably it will be like that. I mean, basically I just made computer to be this axis and science to be that axis. Right? Okay? And then, you know, I can also have a third document, D3, which is just 3 computers. And a fourth document, D4, which is 1 computer and 1 science. All of these can be seen as vectors, right? So the third document, basically 3 computers, so it will be like this. Okay, so 3, 0. And the fourth document is one computer and one science. It's like this. Now, look at these documents and say, I need to come up with similarity matrix here. Okay, obviously the distance measures between things in the space. Okay, the most obvious similarity measure you can come up with is Euclidean distance between points. Okay, so I can just compute this distance. That would be, the more the distance, the lower the similarity. Right? So that's one idea, Euclidean distance. What other idea do I have?
Angle between them.
Angle between them. Okay, which is basically, I would like to say these two are very similar. And one way of saying this is that their angle is close to 0. If the angle is close to 0, I want to say they're very similar. So do you know of any function which when the angle is 0 becomes 1? But there are many, but cosine is a good measure. Okay? So the cosine-theta metric. In fact, Euclidean distance, when you're thinking in terms of Euclidean distance, there is another distance called the dot product distance. And a dot product distance essentially is, if I give you a vector 4i plus 5j, where I guess is computer and j is science, and another vector 3i plus 2j, then the dot product is basically 4 times 3, 12, plus 5 times 2, 10. That's the dot product. That's 22. Okay? So if you don't like Euclidean distance, for example, you can consider dot product distance. And then you also jump to cos theta distance, cosine theta distance. But what can you say that's good about cosine theta distance as against, let's say, Euclidean distance?
What about 1, 1, and 12,
1, 1, and 12, 12. What's
Yeah.
That's the thing, which is basically, we said, really, you can think of this 12, 12 guy as the 1, 1 guy repeated 12 times over. And we do not want similarity to be increasing or reducing. Okay? So, basically, if you do that, then essentially 1, 1 and 12, 12, the distance between these 2 points is this much. And yet you want to say it's 0. Right? Right? Okay, so how can I normalize this Euclidean distance?
Have a base vector.
Just take the unit vector in the direction. Okay? Right? So the normalized, remember again, this is from your linear algebra time. Okay? So what is the unit vector in this direction? 4i plus 5j by 1 of 16 plus 25. Square root of 16 plus 25. That's the L1 norm. That's the Euclidean norm of the vector side itself. Basically, all you are finding is the distance from 0, 0 to the tip of the vector. Okay? And if you divide that magnitude, I mean the vector by its magnitude, then you get the unit vector in the same direction as that vector. Now if I start considering the Euclidean distances between the unit vectors corresponding to two documents, then I will get normalized similarity measure.
But then that's almost like finding the angle.
Well, it's almost, but not exactly the same. Okay? So if I do the same thing, so if I get two unit vectors in the direction of those 2 documents and compute the Euclidean distance, that's a normalized Euclidean distance measure. Normalized Euclidean distance measure. The other possibility is do the same thing for the dot product. Normalize the dot product too, because dot product also depends on the size. Okay? So what I would do is I would take the dot product divided by the magnitude of the vector v1 times magnitude of the vector v2. Yes?
It's not going to give you the opposite of what you want?
No, that gives me exactly, I mean, well, it gives me something, and it turns out it's, what?
If you have just computers and just science and you cross them, you'll end up with... No,
Dot product will be 0.
Just kidding, yeah.
The most beautiful thing about dot product is that when a dot product between two vectors is 0, what does that tell us? This is linear algebra. They're perpendicular. They're perpendicular. Right? Okay, so there is one game that we'll play here. One is that you tend to, when I say a vector, you tend to think in terms of vectors in 2 dimensions. Those of you who are more adventurous may think of vectors in 3 dimensions and make some mistakes. All of you would make mistakes when you think of n-dimensional vectors. Our intuitions are pretty darn bad about n-dimensional vectors. Okay, that's a little, I want to make that, that digression because you want to keep that in mind, which is n-dimensional intuitions. For n to be much larger than 3. Because remember, here the n-dimensional intuitions we need is 6-dimensional. For a normal document, you need essentially the size of the vocabulary in which the document is written. So you're talking about million-dimensional documents. Okay? So here is my question. So since I'm into fruit, let me think of 3-dimensional apple, which you know, right? Suppose I have a peeler and I peeled the 3-dimensional apple. What percentage of the apple's volume is still left? Close to 100, right? Otherwise, why the heck would you peel apples, you know? Right? Do you understand what I'm just saying? So you took your apple and you didn't want to eat the, I guess the peel, so you peeled it. And what percentage is left? So the fraction, the percentage of the apple left, the fraction of the volume of the apple left divided by the volume of the original apple. That's close to 100%. Agreed? What do you think if I do the same thing for a million-dimensional apple? What's your intuition? What would be the amount of volume that would be left after you peeled a million-dimensional apple? But remember, the point about peeling is this. Suppose I have an apple. By the way, 2-dimensional apple is just a circle. 3-dimensional apple is the apple. Okay? So when I say peel, unless you have one of these really bad peelers, I hope that you peel about an epsilon. Just an epsilon thickness. Right? Okay? So I'm only peeling an epsilon thickness. And everything that you ever learned is telling you that most of the apple should be left. What would you say if I tell you that you would have 0% apple left if you were to peel a million-dimensional apple? That's what happens. Why does that happen? It's not hard to see. It's just that we don't put 2 and 2 together. I mean, the way we live our lives is we know a fact here, we know a fact here. We make sure that those 2 facts never talk to each other so that we can live a good life. Right? That's true, because if we actually ensure consistency in our head, we will learn something, but it also probably will blow up. And so we make sure that our heads don't blow up. Okay? So here is a fact that you know, which is, if I have this circle and then I cut off an epsilon peel, right, the amount that is left is r minus epsilon radius. The area of the, we are talking about, for 2-dimensional thing, the volume would be area. So it would be square divided by r square. So that means for 2-dimensional case, it's r minus epsilon by r square. For 3 dimensions, it will be r minus epsilon by r cube. For a million dimensions, it will be r minus epsilon by r power million. What's interesting about r minus epsilon by r? It's a number less than 1. You successively exponentiate it, it will drive it down to 0. Do you see what I'm saying? A million-dimensional apple is all peel, no core. There is no apple there. So don't ever peel a million-dimensional apple. Okay? And similarly, another interesting thing is that if you have a million-dimensional space, 2 random vectors, 2 randomly generated vectors, what is the probability that 2 randomly generated vectors are going to be orthogonal to each other? That means the dot product would be 0. it turns out that probability is extremely high. It's low in 2 dimensions because your intuitions are in 2 dimensions. You can generate large number of vectors and say, hey, they are not perpendicular, so the dot product is not 0. In million-dimensional spaces, once again, it turns out that most randomly generated vectors are perpendicular to each other. So aren't you happy that the documents are not randomly generated? Right? If they were, then all the similarities in the vector similarity would be 0. So you're just picking which 0 is better. Yes?
You're calculating the amount peeled or the apple left?
Apple left. I mean, I'm assuming that most of us peel so that we'll eat the rest of the apple. What I want to know is how much apple is left. So what I'm looking at here is, this is the r minus epsilon q for a 3-dimensional apple is the volume proportional to the, this is the volume of the apple left as a fraction of the original apple. And the only thing that matters is r minus epsilon by r is less than 1. However little less, it is less. And you exponentiate a number less than 1, indefinitely, you will get a 0. That's just as good as a. And this is not surprising. You know this. But you don't put it together with that. But that's how we live. We don't necessarily. Intuition essentially is our ability to not put together our knowledge completely. Right? And so our intuitions about n dimensions tend to be wrong. So, however, mostly I will think in terms of vectors, vector spaces, and the mathematics of vector spaces is the same in n dimensions too. But your intuitions may or may not go. That's how I say. Okay? So, now going back to the dot product distance, if I divide the dot product distance by the 2 magnitudes, what do I get? It turns out that is actually cos theta. That's again linear algebra. If you have 2 vectors, v1 and v2, you take the dot product of those 2 vectors, divide it by the magnitudes of those 2 vectors, that will be actually equal to cosine theta. So cosine theta is really nothing but normalized dot product distance. Look at all the beauty of connections. Cosine theta is nothing but normalized Euclidean distance. I'm sorry, normalized dot product distance. Okay? So now the question is, what's the difference between cosine theta, which is normalized dot product distance, and the other one that I talked about, which is normalized Euclidean distance, which is 2 unit vectors, and then take the distance between the 2 things. Clearly, it's somewhat kind of connected to theta, but it's not exactly the same. Okay. The interesting thing is, I'll show you a picture basically later on. In general, people have done an experimentation and found that the cosine theta similarity metric tends to capture people's view of similarity between documents better than the normalized Euclidean distance similarity. And this is the kind of thing I can't easily prove, so I'll show you a picture. Apparently, picture is worth 1,000 words, so I'll show you. Okay? So that's basically the lecture for the first half of the class today. And then I need to kind of run through the slides which say the same thing except on the slides. Okay? Okay, so this vector model. So each document is a vector in some n-dimensional space. Now, obviously, we are assuming that each keyword is a dimension. And normally, we assume that all dimensions are perpendicular to each other. Right? And so there are orthogonal dimensions. Now what that means is that all the keywords or all the words in the document are independent of each other. Okay? Now what that basically means is whatever I tell you about how many times a particular word is present in a document, you will never be able to say anything more about whether or not this other word is going to be present in the document. Suppose I asked you, what do you think is the probability that this document I have in my hand has the word science in it? Suppose you just made 0.3. 0.3 is the probability for whatever reason. Now I'll give you some more evidence. I look into the document and say, hey, I think this document seems to have 18 instances of the word computer. Would you like to change your probability? Okay? If you were to change your probability, that means computer and science are not independent. Okay, because that's again the definition of conditional probabilities. That's the definition of conditional probabilities, right? So A and B are independent if PA given B is the same as the other. So how much ever I tell you about how many instances of computer are there, you don't change your mind about what the probability of science being present. If you think this is true for every pair of words in the world, then you can actually say vectors can be really seen as, these can be seen as vectors in n-dimensional space with n orthogonal bases. If you don't, then you know that you are making a gross simplification. But then this is not the first time we are making gross simplifications. We started with an English document and said it's just a bag of words or a vector of words, which lost a lot of semantics of the document anyway. So it's just one more mistake we'll make, one more simplification. Okay, so the question is it a reasonable assumption? Is it reasonable to assume that all words are independent? Actually, it's not. But all you need to do is to do better than your competitor. And it turns out that if you compare vector similarity metric to Jaccard similarity metric or Euclidean distance similarity metric, it does just as well. No worse, no better. More or less in the same ballpark. Okay, however, as I said earlier, the vector similarity with the vectors as the semantics of our documents, we can use linear algebra and reason about dependence and independence between dimensions. And one nice technical topic we'll talk about maybe a week, 2 weeks from, maybe a week and a half from now, is latent semantic indexing, which is essentially figuring out that even though you think there are 3 words really with 3 different dimensions, what you really have is 2 dimensions, because the third dimension is just a linear combination of the first 2. Do you understand what I'm saying? Okay? So we'll talk about that then. So, but keep that in mind, that this is an assumption we're making. Then, so the query will be a vector, and the document will be a vector in the space, in the same space. And then you want to compute their distances. This is an unnormalized Euclidean distance. You can normalize it by taking the unit vector in those document directions. You can also compute unnormalized dot product distance, which I mentioned. Okay, both the unnormalized dot product and unnormalized Euclidean have this problem that they depend on the length of the document, not the distribution of the words, but the length of the document. If you normalize it in any which way, by so that the length doesn't affect, then you will have normalized measures. Okay, so you have a normalized Euclidean measure and then the normalized dot product measure, and the normalized dot product measure is nothing but cosine theta similarity measure. Okay, that's basically it. And then so cosine theta similarity, when theta equal to 0, then the two vectors are the same, and so they are identical as far as you are concerned. And so cosine of 0 is 1, so similarity would be 1. If the 2 documents are perpendicular to each other in this n-dimensional space, then it would be cos of 90 degrees, and you would get 0, which is the similarity. Why can't it be 270 degrees between the documents? Why can't it be 320 degrees between the documents? I mean, again, you're all coming, at one point of time you did, yes?
Because you can't have negative instances.
Exactly. Okay, math applied to your application. Okay, this is math, but you will not have 270 degrees between any 2 documents because you're stuck in the first quadrant. All your vectors are in the first quadrant. Because you cannot have negative 3 instances of computer in this document. Do you see what I'm saying? Okay, that's why you really need to get between 0 and 90, that's it. Okay, fine. So, if I were to consider this example, remember this example I mentioned that these first 5, remember these are the terms, T1, T2, T3, up to T6. These first 3 terms are database, SQL, and index. The last 3 terms are regression, likelihood, and linear. Okay, and as I said, in some sense, these first any document which has mostly these first 3 terms is probably a database document, and any document that has these three terms mostly is probably a statistics document, I hope. Okay, and notice that I'm thinking of indexing the document only in terms of some of its words, just the keywords. That's fine. You know, the theory works whether you index it in terms of keywords or all words. Okay, so that's the case, and so what I want to now find is I can compute the document-to-document similarity matrix. So there are 10 documents. I want to compute di dj similarity for each I and j. Now obviously this matrix, similarity matrix will be symmetric because I is as similar to j as j is to I. I mean all the similarity matrix we have done till now are like that. Okay, so if I were to then compute that, and then I were to draw this picture such that if the similarity, remember similarity will be, I'm only looking at normalized ones. So similarity is between 0 and 1. And so if I look at similarity close to 1, I will make that point to be white. Okay, and if it is 0, I'll make it black. Anywhere between 1 and 0, I'll make it different shades of gray. Okay, so I will then show you a picture of the document-to-document similarity matrix. Okay, and so all this is basically saying is anything that's white, that means they're very similar to each other. Okay, now this document, and then anything that's dark, that means it's not really that similar to that document. Okay, so for example, this is D5, this particular thing is 5 and 10. So this is a representation of the similarity between document 10 and document 5. And all this is saying is they're not very similar at all, according to Euclidean measure. And this picture shows the same thing, except the distances are not computed. The similarities are computed using vector similarity. That's it. So which would you like? You like Euclidean? Why? so the thing is, so first of all of them will have white on the main axis. That's not surprising because if you are not similar to yourself, you have major identity problems. Right? Okay. And so everybody will this thing. The real question is, notice that cosine theta basically says all the first 5 documents are more similar to each other. Okay? And then it also shows, for example, that the D5 to D10 are less similar to each other. And so in some sense it smooths over the similarity and is able to capture your intuition that these guys form sort of a cluster and these guys form a cluster. Whereas the Euclidean sort of splits hairs. It is saying between, so in fact the way Euclidean is going, you can very easily, I mean suppose you notice that you have squares here which are of the same sort of a color as the squares here, which means one of the documents here might actually be more similar to a document from the statistics side than it is to other databases side. If you think that's a feature, then you like this. If you think it's a bug, then you don't like this. Okay? Most people think that this is a feature that's a bug. In the sense that in this particular example, you really like your ranking to be able to see that the database guys are more or less close to each other. There may be small variations, but they're much more close to each other. So the idea is somehow within a cluster there may still be distances, but the distances within the cluster better be smaller than the distances across the cluster. That's something that's captured. So this is as good an argument as you can ever get as to why we like cosine theta similarity metric as against normalized Euclidean distance similarity metric. This is it. I can't do anything better than this. Okay? The rest I could have said, if you don't agree with this, then I say everybody just uses cosine theta similarity metric. That's pretty much what they do. Okay? And the second question is why cosine theta, why vector versus back, I already told you. Because vectors allow you to generalize the interpretations to handle independence of vectors, which will come very soon. Okay? Okay, so that's basically between these. And so after this slide, then I just assume unless I tell you otherwise, when I say distance between two documents, I'm going to compute it using cosine theta similarity metric. Okay, that's what I'll assume. Okay, you should know all the pluses and minuses of the various things, but for the class we'll stick with this. Okay, and then of course, if I'm computing the distance between the query and the document, then I think of query also as a mini document. It's a vector in the space of in the same space as the document is, and I compute the distance between these two vectors. Okay, right? So here is an example what we are doing basically. So my query is database and index. And remember that my terms are T1 to T6, right? So if database and index, then 1, 0, 1, 0, 0, 0. That's what it should be. 1, 0, 1, 0, 0, 0. That's what my vector is. Okay? This is my vector, and each of these documents are their own vectors. This is just unadorned, view of query as a vector in the same space. Okay? And now I can compute the cosine theta similarity metric between these, and then I will notice that the numbers I get, if I just plug it, these are the vectors, and this is one more vector for each of query and each of the documents. I compute the cosine theta similarity. It's just plugging it to that formula. It is dot product divided by the magnitudes of both the query and the document. Okay, if I do that, then I will get 0.70, 0.77, 0.58, 0.60, 0.79, 0.14, 0.06, 0.02, 0.09, 0.01. Now, one of the homework problems would be for you to confirm this, that is actually true, that if you were to just plug it in. I know that it's correct, but if you plug it in, you will know for sure. Okay, so now the interesting thing is that, first of all, you do see that the first 5 are much closer to the query than the last 5, which sort of is with respect to your intuition that database index query is closer to database things than the statistics ones. Okay, so and then the other thing is that if I were to rank them in the order of their similarity, I would say D5, then D2, then D1, then D3, then D4. That's my top 5 documents. So you have your search engine now. So you have a query, you have a way of computing the similarity, and you know how to do sorting. Right? Okay, so the rest of what we'll do here is how to improve this a little bit more in terms of the similarity computation, one part. And the second part is how to represent the documents and queries in the computer such that this operation would be as efficient as possible, because you could do it quite badly. That's the inverted indexing approach. Okay, and if you understand those two, then you will be able to do project 1. I also kind of understood like the first important part of IM. Right? Okay. Any questions? Yes. Yes. I'm sorry.
Again, it depends on the number of words present in that document. It is.
No, right now I did not. All I did is remember that each document. Remember that I'm doing normalized. That means the query has a certain length. Each document has a length. After I compute the query and the document's dot product, I am dividing it by the query size and the document size. So in a sense, I am making some amends for the size of the document. It turns out that's not enough. That's what we'll talk about next minute. Okay? But we are taking into account the size of the document. Okay? To do the next part, you need to understand a little bit more about how words are distributed across, documents. Yes?
So going back to the picture you had, Euclidean would be seen maybe as week4 and cosine as precision.
I don't know. No, I think you can get precision and recall for both of these, because if you want to get top 10, I will give you all top 10. It's just that the lowest one has very low similarity. Unless you put an artificial threshold and say anything below that similarity is not at all a result, I will give you all the results. The real question is the order in which I give them.
Yes.
So what Euclidean is likely to do is it will probably give you in the top 5 some statistics. I mean, given this picture, I would think that Euclidean is likely to give you some statistics documents interspersed in the middle of database documents in the first 5. Again, all of this, I'm saying it as an oracular fashion. First of all, you should all know, this use of the word oracle. The other day, I even tried to crack something and nobody understood. It's not the oracle of Larry Ellison, but it's the Delphic oracle. Okay, an oracle basically knows everything. It's better than the user and the system. It's like all-seeing seal. Okay, and we compute precisions and recalls and the right way of ranking, etc. from this oracular sense. In normal time, when you give a query, you will get some number of documents. You don't know which one is better. You just, you'll say that my similarity metric gave me these documents. And what's even more pernicious, and at some point in time I'll tell you this, that if you try to actually evaluate what users consider relevant, it's not even clear whether users have any idea what is relevant. In fact, there was a study where people were trying to check whether the fact that Google gives a result at the top means the user thinks that must be what they're looking for, which is kind of pushing everything upside down, right? I mean, you should be looking for something, and then you see whether Google is giving it. But a sufficiently effective technology can make you feel the other way around. Maybe I shouldn't have been looking for that other thing. Google says this is what I should be looking for. And so there was a very carefully constructed study that has been done by at Cornell, where essentially what they did was they considered Google's top 10 always, except in one case, without telling the users. In one case, it's just the Google's top 10. In the other case, they just changed the order of the top 1 and 2. And users consistently like the top 1. That's what we really wanted, which they couldn't have read, right? Because obviously we're changing the order. What does that mean? Because we just assume that Google knows better than us. So whatever I'm asking for, they will tell me what I really need. Now, all those issues also come into these oracular studies. Who is to tell? If the user is very happy, then can you tell them that you shouldn't be this happy? And you can't make too much money, telling people to be unhappy. Okay, but that's the issue of ranking. And in answer to your question, you can rank these. It's just that you may get interspersed some of the database and statistics documents, and you will never know. In this case, you can tell. But this is just an illustrative example. This is not a proof. Yes.
My question, and it might be too early. Like, I know we were saying we were going to go over efficiency and stuff, but like the thousands and thousands of documents and thousands of words, these calculations would take forever.
Exactly. So we'll do it faster. That's what indexing and retrieval is all about. Okay. All sorts of things have to be done, but we'll do at least some. Okay. Yes.
No, I just wanted to know why the cosine gave a distinct black and white color and.
I don't know. I just plotted it. I don't look like a cosine to you, right? So I don't know what it does. This is what it is. That's the interesting thing. Since it does it like this, then we should like it. That's the nice part. Okay, it's able to actually tell. So think about it this way. I mean, I always felt that there should be as many grades as there are number of students in the class. Why my life would be very simple. Okay, and I'm slowly getting there. When I first came to USU, there only used to be A, B, C, D, E. That's it. Now there is A plus, A minus, B plus, B minus, C plus, C minus. No, there's C minus. There's no D plus apparently. There's just D and then F. Okay, so I have more people. So if I can make enough of you drop so that there are as many grades left as there are people, then I don't need to do this hard work of what is this mark supposed to be in the letter grade. I'm trying to look for equivalence classes. Anybody can say these 10 are different documents. The question is in how many equivalence classes are they falling? Anybody can tell that the 47 or so students here are all individuals. The question is, can I put them in some reasonable equivalence classes? Okay, and so you don't want to believe that being able to split hairs is a feature. It could be a bug. Me telling everybody that their social security number is their grade, and that way everybody will be unique. Okay. So, but the fact that it's actually seeing the equivalence classes is an argument in its favor. Okay. So this is fine. This is just directly with respect to terms. So the two other aspects that you want to consider is, yes, these things are normalizing with respect to the document length, but they do assume that all words are created equal, both within the document and across the documents. And so what you really want to do is, if for example, a document has 25 instances of the word computer, but then its total number of words is 5,000, that's different from another document which has 25 instances of the word computer, but the total number of words there is only 100. Okay, to some extent this is what you think normalization is supposed to capture, but really what I want to know essentially is which words in these documents are really important words, which are indicative of the true class of this document. Believe it or not, when we used to think in terms of keywords, librarians used to think in terms of keywords, one can argue that keywords are less dependent on each other than normal words are, because keywords are a very small subset. I am any day going to believe that there are about 1,000 orthogonal categories than to believe that there are about 10 million orthogonal categories. So coming up with keywords, basically, somebody comes up with keywords, they probably already made sure that they are enough different from each other. So what I really would like to do is sort of, rather than just look at the raw frequencies of words, somehow normalize the frequencies of words themselves, such that they tell us this following information: how indicative this word is of this document. Okay? Now, how indicative of this word is of this document? So, I am standing in front of you. Give me some features that I have right now. For example, I have a t-shirt. Clearly indicative. If I remove my t-shirt, you'll all run, and it's sort of indicative of me. Right? Is that a good? And I also have 10 fingers. So it looks like my fingers are more indicative of me than my t-shirt, which is only one. So Rao has 10 fingers, one t-shirt. So somehow fingers are more important than shirt. That's how we are looking at it. Okay. Now first of all, think about this. Is my t-shirt indicative at all? Are my 10 fingers indicative? No. Everybody has 10 fingers. It's like a Martian coming to this universe will think, this world will think, all of you are so boringly alike. Okay, you all have the same number of eyes, same number of noses. Where is the design freedom? Why not a few extra eyes and a couple of extra noses? This, infinite number of possibilities of design. Looks like, you guys evolved in a reasonably boring fashion. Okay, so most of the things that we share with each other are useless in distinguishing us from each other. So what do? The first thing we do when we grow up, we start ignoring the things that we have common with each other. So as soon as the first standard teacher tells me we're all created equal, we should share, etc. After that, we'll ignore that and we'll say, that person has a much bigger cookie bag than I do. That person has something. The important thing is the differences, not what we share. So my t-shirt is useless because you do have one. This, on the other hand, is extremely useful because none of you seem to be sporting one of these. Do you understand what I'm saying? Okay? And so if I want to blend in, I should avoid wearing shirts like I shouldn't wear, for example, full Indian formal regalia and walk around in Mill Avenue and expect that people will sort of think I'm just born and bred Arizona. Right? Why? Because I'm looking different. I basically made sure that my features have no connection with anybody else's features. If I want to blend in, I will basically try my best wearing the same sort of thing everybody is wearing. How many of you know the Alibaba and the 40 thieves story, where the thieves come and basically the next day they're going to come to Alibaba's home and the next night, so that during the daytime they go and put a cross on the house they know is Alibaba's. So the night they will come and do bad things. Right? And then Alibaba's girlfriend, who took IR course of some sort, basically what does she do? What does she do? She doesn't remove the cross. Removing the cross is silly because if you remove the cross then you will leave some marks. Okay? All she does is puts the same cross every day. That's it. Okay? So, if you have the same feature as everybody, it's useless feature. First things first. It's true that it kind of gives us some kind of a kumbaya notion that we're all together. But we are not into kumbaya when we're doing, IR. We want to see this document is somehow better than this document for this query. So each of them should advertise themselves on their distinguishing features. Okay? So the first point I made is if a word appears in every document, it is useless. So a word that appears in this document that doesn't seem to appear in most other documents is much more useful than one which appears in everywhere. Okay, so what I would like to think of there is this notion, I want to take number of documents with the number of documents in the corpus divided by the num documents having word W. This is sort of the importance of the word is proportional to the number of documents in the corpus divided by the number of documents having that word. So if in fact only one document has that word, then this would be a million documents in the corpus by one. So it's million important. If everybody has that word, then million by million it will be one. It will be one important. Okay? Got it, right? So all I want to do now is play with that intuition and say, I want to make 1 to be 0 and million to be a little smaller. What do? Find a monotonic function which cuts down the magnitudes, logarithms. Okay? So if I take log of this, it has all the properties we wanted. Right? So log of this would be large for log of million. So, and it's still larger than log of 1, which is 0. Okay, so one importance idea is this measure. I would go with this measure. Log of number of documents in the corpus by the number of documents which have this word. And this measure is called IDF, inverse document frequency. It's actually log of the inverse document frequency. Okay? Yes?
What were the numerator and denominator?
So suppose I have a million documents, okay, and the word computer occurs in 25 of them, then the importance of the word computer, in fact the IDF of the word computer is equal to log of 1 million by 25. Okay? Again, you will have enough time to make sure that you got the formula right. The most important thing is, you know why the formula makes sense. If it makes sense, these are simple formulas. You can write them. You should never do it the opposite way. Because if you do it the opposite way, then you are saying, if everybody has that feature, then it's a good feature. Well, it is a good feature to talk about what. So here's the interesting thing. Suppose if Martians were to go back to Mars, and they have made a trip to Earth, looked at us. They went to planet Uranus, looked at people there. People-like thing is there. And then they went back to Mars and they're writing, like, here is a description of humans. It's a description of, Uranian people. Okay? They better not say the most important feature is that one guy has this. It's useless. What makes me unique is also the most useless characteristic of the common human experience. What they really are going to say is all humans seem to have 10 fingers, just 2 eyes and one funny nose in between them, and they all think as if they're different from each other. That is also universal. We all think we are unique. Okay, despite all these common things that we have. So that's what you would do to describe the entire cluster called Earth. The cluster description would need to consider, for example, words that are more common for that cluster and less common across clusters. So if in fact it turns out that people in Uranus also have a nose but only have one eye, then the two eyes is a better description of Earthian people than one nose, because one nose everybody seems to have. It's the same idea. And I'm not really into interplanetary science here. You will eventually write clusters. You will find clusters and you will write descriptions of clusters. Remember when Google gives you like a synopsis of a page, right? One of the most interesting questions is, when it gives you a document, the best thing it can say is the results are document number 78958985, document number 83848578, etc., the top 10. And what is there not to like? And by the way, first part of your project will let you do that. And then basically, because that's easier to do, just give the document identifier as the result. What you want is a quick description of the document before you take the time to click on that document. If you're going to click on the document anyway, I told you, you should believe me. And if I tell you that D78597875